Hello, so in this section we're going to look at differentiating quadratics, right? So expressions that look like y is ax squared and bx plus c. For example, y is, say, 2x squared add 4x minus 7, right? Any quadratic, right, in that way. So we're going to differentiate it, so we're going to find what dy dx is. Okay, so if we're given a quadratic, what would its derivative be? That's what we're going to look at, and really it's basically the power rule. So again, make sure you saw last video or how you differentiate powers of x. So remember when we looked at if y is equal to a power of x, so x to the power of n, then the derivative or the gradient dy dx is the power n is moved in front, then x, and then you knock 1 off the power, n minus 1. That's my power rule, okay? And we will be using that in this section too. Now, quadratics. What do quadratics contain? They contain an x squared term, they contain an x term, and a constant, a number, right? So, let's consider then, if y is equal to x squared, what would the derivative be? Dy dx. Well, we do the same idea with the power rule, right? So we're going to bring the power 2 to the front, then we're going to have x, then we knock 1 off the power. 2 minus 1, which is 1, okay? Or x to the power 1 is just x, right? Anything to the power 1 is just itself. So in general, if we have x squared, then the derivative is 2x, okay? Via the power rule here. If we had y is just x then the derivative, well, what's the power x here? What's the power of x here? Well, it's just x to the power 1, really, right? Remember, if it's just a number, it's technically raised to a power 1, right? There's a hidden power of 1 there. If we use that idea then the derivative is going to bring the 1 to the front, 1x, then we knock 1 off the power, 1 minus 1, right? Well, what's 1 minus 1? It's 0, right? But hang on, we can simplify this, because what's a power? What is anything to the power of 0? Remember, a to the 0, any power, and any number a raised to the power of 0 is just 1. So therefore x to the 0 is 1 as well. So it's 1 times 1, which is just 1, right? So overall we just get 1. So that means then the dy dx then, if y is a power of x, if I just get rid of all this now, if we just have a power of x, if we just have x then the derivative is 1, okay? Okay, then lastly, what if y is just a number, right? Let's say y is a number, a constant, right? C, right? A constant. Right, so a constant being a fixed number, so it's not x, right? Basically, it's just a number, but it's just a hidden number, right? C could be 2, it could be a half, it could be minus 7 over 100, any number whatsoever, but it's not x, right? It's not a variable, it's not x, right? So it's just y equals some number. See, well, actually, we can actually make this a power of x. We can be quite clever with this. We can rewrite y as c, or number c, as actually then x to the 0, because actually x to the 0 again is just 1, because this is saying c times 1, but any number times by 1 is itself, right? So we can be quite clever and say that if we have a number c, we can just say cx to the 0. Then we can use the power rule, right? So then dy dx is going to be, well, we're going to bring the power to the front, right, at the 0, so it's going to be 0c times by x, and then we're going to knock 1 off the power. 0 minus 1, which is 1, minus 1, right? But none of that really matters, because really what we've then done is multiplied everything by 0, because we brought the 0 to the front. That just goes to 0 overall, right? So therefore, if you have any number, any constant c, right, no x involved, if it's just a number, we can differentiate it and it goes to 0. Okay, so for example, if y equals 3, then it goes to 0. Okay, any number is 0. If y is 3, it goes to 0. If y is 10, it goes to 0. If y is just minus 17, it goes to 0. If y is minus 7 over 800, it goes to 0. Any number whatsoever always differentiates to 0 because of this idea here. Okay, so we're going to use this idea then, right? So we know how to differentiate these powers of x then, x squared, x, and a number, right? So we're going to use this then to do some examples. So we need to find dy dx given that y firstly equals y is x squared and 3x. Now, you may notice we're adding two terms of x, right? We can't combine it as one power of x. We can't do that. We're always going to have to add. But if we're adding, we can differentiate the terms individually, right? And it works how you kind of expect. So therefore, if we were to differentiate, we can differentiate term by term. So firstly, we have x squared. If we differentiate that's going to be 2x, right? Because it's going to be the 2 goes to the front, so it's going to be 2x. Then we knock 1 off the power, so 2 minus 1, which is just 1. Well, actually, that's just x then, so that goes to 2x. And then we add, then we differentiate the 3x, right? Well, 3x, that just goes to 3, right? Because, again, the x has a power of 1. That 1 is just brought to the front. So we have 3 times 1, which is just 3. X to the power of 0, because we knock 1 off the power, because it's 1 minus 1. But then that's just itself, right? That's still 1. So we just get 3, okay? So again, the other idea is eventually, basically, if we have x, it just goes to 1, right? So then we have 3x, that goes to 3 when we differentiate. And that's it. Okay, that's a differential. Now part B, we have y is 8x minus 7. Now, dy dx, 8x, the x goes to 1 when we differentiate, so it's just 8, okay? 8 times 1, which is 8. Then with subtracting, we'll be differentiating minus 7, right? So we're going to differentiate minus 7. That's just a number, and we saw up here that any number differentiates to 0. If it doesn't have an x, it goes to 0. So it's 8 plus 0, but it's just 8, okay? So actually that tells me then the derivative is always 8 in that case. Part C, we have y is 4x squared minus 3x plus 5. So the differential, in this case, a different derivative, well, 4x squared, well, we're going to have 4 times by, then if we differentiate the x squared, that goes to 2x, right? Then if we differentiate minus 3x, that goes to minus 3. And then if we differentiate the 5, that's nothing. So it's plus 0. But we don't need to include that, right? So if we do some final simplification, 4 times 2x goes to 8x, and then minus 3. And there we are. Okay? Cool. Right, okay. Okay, now we've got this example. We have f of x is 4x squared minus 8x plus 3. We firstly need to find the gradient of y is equal to f of x at the point half 0. Now, the gradient at a point, what we can do is we just find the gradient, the derivative as we expect. So if f of x is equal to this, then the derivative f dash of x, that's going to be then, if we differentiate all these terms, of 4x squared, what we can do as well, we can just multiply the power by 4. So that'd be 8x, okay? Because again, we knock 1 off the power, because then 2 minus 1 is 1. So that's just x. And 4 times 2, because we bring the power 2 to the front, it's basically 2 times 4, which is 8. Then minus 8x, that goes to minus 8. Okay, then plus 3 goes to 0, and that's it. That's my derivative there. Okay, now that's my derivative. Now it wants a gradient, which again, this is the gradient really, but that's for every value of x, right? it particularly wants the gradient at the point half 0, okay? Well, actually, we need to substitute x is a half, right? So I'm going to say at x is a half, f dash, instead of f dash of x, we're going to plug in x as a half in, right? Then if we plug in a half for x into my gradient here, that's going to be 8 lots of a half minus 8. Then that will get me minus 4. Okay, and so therefore that tells me when x is a half, when we're at this point on the curve, the gradient is minus 4. Okay. So yeah, if you then have, if you want to find the gradient at a point, we can differentiate to find the overall gradient for all values of x, then plug in the value of x you want to get the gradient at that point. Part B then says we need to find the coordinates of the point on the graph y is equal to f of x, where the gradient is 8. So now it's kind of doing it in reverse. They're telling us what we need our gradient to be. Well, our gradient overall is 8x minus 8. What we then need to do is, because it's told us the gradient needs to equal 8, it needs to be 8, we can equate this to 8, okay? So f dash of x needs to equal 8, so therefore 8x minus 8 equals 8, okay? Then we need to just solve this equation, because then that will give me the value of x. So then 8x, if I add 8, equals 16. If I add 8 to both sides, then x, if I divide by 8, we get 2. Okay, so that's telling me the x point is 2 when the gradient becomes 8. But then remember, it told us to find the coordinates. The coordinates is xy. We need a y coordinate as well as an x one. Okay, so coordinate. Well, the coordinate is going to be xy, but we know x is 2, so it's going to be 2y. How do we find the y coordinate then? Well, we're given the original function, right? That's f of x. So we can find y by substituting x is 2 into it, right? So then y is going to equal my expression, my 4x squared minus 8x plus 3. But then when x is 2, we get that it's 4 lots of 2 squared minus 8 lots of 2, add 3. Then if we put that in the calculator, we get y. Y to be 3. Okay, so therefore the coordinate, the specific coordinate is x is 2, y is 3. Okay, so so this is a good question to not be confused by what you're substituting, by where you're substituting things into. Okay, you do not substitute x is 2 into this gradient function. This is the gradient of my curve. Okay, the original curve is this. Okay, so if I want to find a point on the curve, I need to be using my original function, because that's the actual curve. F dash of x just tells me the gradient, okay? So be very careful. So anything to do with gradients is f dash of x, but if you need to find coordinates, then you need to use the original function. Okay, anyway, part C, we now have the gradient of y is equal to f of x at the points where the curve meets the line y is 4x minus 5. Okay, so we're told that the curve, now again the curve is this. It's this original expression here, f of x. So this curve meets this line. Well, actually, this seems like simultaneous equations, right? Because the two things are intersecting, right? The curve and the line. So that means y, firstly, is this 4x squared minus 8x plus 3. That's my function. We're also told that it meets the line y is 4x minus 5. This is simultaneous equations, right? I can substitute one equation into the other. Okay, so therefore 4x minus 5 in replace for y would equal 4x squared minus 8x plus 3. So I've substituted one equation into the other. Then I can rearrange, right, to get a quadratic, right? So it's going to be 4x squared. Then if I move 4x to both, if I subtract 4x to both sides, minus 8x minus 4x will be minus 12x. Then if I add 5 to both sides, I get plus 8 equals 0, okay? Now this is a quadratic equation. I can actually divide by 4 to simplify, actually, if I wanted to. If I divide everything by 4, I get x squared minus 3x add 2 equals 0. Okay, and then I can solve it, and then obviously this is a quadratic equation. I know how to solve. You can pick your poison, pick however you want to solve it. Maybe you can factorize. So again, if you're factorizing two numbers at times to get 2 and add to get minus 3, well, actually it'd be minus 2 and minus 1, right? Because minus 2 times minus 1 is plus 2, and if you add them you get minus 3. So my factors are x minus 2, x minus 1 equal to 0. So therefore x is 2 or x is equal to 1. So I've got two x coordinates, two x points, but I need the y. I can substitute the x values into here then. Y is 4x minus 5. So that means when x is 2, y is equal to 4 lots of 2 minus 5, which would be 8 minus 5, which would be 3. That gives me the coordinate then, 2, 3, or x would equal 1, right? So if x is equal to 1, then y would equal 4 lots of 1 minus 5, which would be 4 minus 5, which is minus 1. So therefore I get the point 1 minus 1. xy is 1 minus 1. So I've got these 2 points then, right? These 2 points. But they didn't ask me to find the points. They asked me to find the gradient at the points. So what I need to do then is to substitute my point into my gradient function here. Okay, so if I restate this, f dash of x is 8x minus 8. Well, I've got these 2 points here, right? X is 2, x is 1. I need to substitute both x's in. So when x is 2, f dash of 2 is going to be 8 lots of 2 minus 8, which would be 16 minus 8, which is 8. Okay, so my gradient, my corresponding gradient is 8 at that point. Okay, then I need to find the gradient at this point, which is when x is 1. If I substitute x is 1 into my gradient function, my gradient at that point is going to be 8 lots of 1 minus 8, 8 minus 8, which is 0. Okay, so that tells me then the gradient at this point is 0. Okay, and there we are. Cool. Okay, now we've got some more exercise questions. So we are told to find the gradients of the curve y is 2x squared at the points C and D, where the curve meets the line y is x plus 3. So it's a very, very similar question. Okay, pretty similar to what we just did. Now this curve, we're told, meets the line at these 2 points. So again, that's simultaneous equations because the curve is meeting or intersecting the line. So I can solve them, right, simultaneously. If I substitute one into the other, I get x plus 3 is equal to 2x squared. Then 2x squared minus x minus 3 equals 0. Okay, I can solve this quadratic again. I'm going to use the formula now. So x is going to be plus 1 plus or minus the square root of minus 1 squared minus 4 lots of 2 lots of minus 3 all over 2 times 2, and so therefore my two solutions are x is 3 over 2 or x is minus 1. Okay, but then I need the y coordinates too, right? I need my points C and D. So therefore y, well, I can substitute x into either. So y is x plus 3. So then firstly, when x is 3 over 2, y is going to be 3 over 2 add 3. That would be 9 over 2. Okay, so that gives me the coordinate 3 over 2, 9 over 2. Okay. Now, the other solution is x is minus 1. So if x is minus 1, y would then be minus 1 add 3, x plus 3 minus 1 add 3, which is plus 2. So that gives me the point x is minus 1, y is 2. So I've got these 2 points again. Now, again, it didn't ask for the points, it asked for the gradients at the points. Well, and that's the gradient on the curve, right? So remember, y is 2x squared. If I'm going to find a gradient, I need to find a gradient function. I need to differentiate this, right? So that means dy dx then, if y is equal to 2x squared, my curve, my dy dx then is going to be 2 times 2, because 2 times the power 2, because that's brought in front, so it's 4x, and that's it, okay? Because 2 minus 1 is 1. If I knock 1 off the power, it goes to 1. So x, it's just x. So 4x is my gradient function. If I bring that down here then, dy dx is equal to 4x, well, I can find the gradient at each point by just substituting the x point in. So firstly, when x is 3 over 2, dy dx is going to be 4 lots of 3 over 2. That would get me 6, okay? And then I can also do it for this, so therefore the gradient at the point x is 3 over 2, this point here, the gradient is 6. And I can do the same for this other point here by substituting x is minus 1. Okay? Oh, hang on. Yeah, x is minus 1. So therefore the derivative at minus 1 is going to be 4 lots of x, which is 4 lots of minus 1, which is negative 4. So then I can say the gradient is minus 4. And there we are. Okay, cool. Okay. Right, now we're going to finish off with an exam question. So we are given this curve again. We did parts of this exam question in an earlier video, but we're going to do the full thing now. And it really brings together everything we've done so far in this chapter. So we are given this curve, which has the equation y is 3x squared minus 2. The point P, which is 210, lies on the curve. We firstly need to find a gradient of the tangent at P. Now again, the tangent, again, will be touching the curve at P, something like this. But we can find that gradient now, can't we? Because we know how to differentiate. So we know the curve is y is 3x squared minus 2. We can differentiate to find a gradient at a point, right? So then dy dx by 3x squared, we basically do 3 times 2, which is 6. And then 6x, and that's it. And then minus 2, any number goes to 0, as we've seen earlier. So that's it. So it's plus 0 or just 6x. And there we are. But, so therefore the gradient, it wants a gradient particularly at the point P. But P is 210. So that's when x is 2, right? So at x is equal to 2, which is at P, then the gradient dy dx is 6x, which is 6 lots of 2, which is 12. And there we are. Cool. Okay, part B. Now part B we did do in an earlier one, but we'll do it again. We're told now the point Q with x coordinate 2 add h also lies on the curve, okay? Which is here, okay? We need to find a gradient of the line P to Q. Okay, so we need to find a gradient from P to Q, right? Now, we won't be differentiating anything in this case because P to Q is just a gradient between 2 points, okay? That's a line. That is going to be changing y, changing x, okay? Okay, so it's going to be changing y, changing x between these 2 points. Well, we know that P is 210. We were given that. P is 210, which is here. And Q, well, we know Q is going to be xy. but we told the x coordinate, right? We told that x at q, the x coordinate is h of 2. Okay, but we don't know the y coordinate, right? We don't know the y coordinate. But again, q, we're given the curve, right? We know what the curve is, so we can substitute x here into my curve to get the y coordinate, right? So then y is 3x squared minus 2, but when x is h of 2, that becomes 3 lots of h plus 2 squared minus 2. Then I just need to expand the bracket. If I do that, I get 3 lots of h squared, add 2h add 2h, add 4h then, add 4, or minus 2. Then I can expand that again to get 3h squared, add 12h, add 12 minus 2. And so therefore that goes to 3h squared, add 12h plus 10. Okay, so there we are. So then I can I've got my y coordinate then, which is this expression, 3h squared add 12h plus 10. That's my y coordinate now. Now I'm in a position where I can do my gradient, my change in y, change in x between p and q. Okay, so the change in y coordinates then, where q is 3h squared add 12h plus 10, take away the y at p, which is take away 10, all over change in x. So the x coordinate at q is h plus 2, take away x at p, which is 2. Then we can simplify, right, because 10 minus 10 goes away. So it's 3h squared add 12h on the top. And then h plus 2 minus 2, they cancel as well. So it's just over h, okay? So there we are, we simplified. We can simplify even more. We can factor a h out. We can factor a 3h out, in fact, on the top. 3h, then h add 4 over h. We can cancel a h out, and I'm left with 3 lots of h add 4. If we expand that, we get 3h add 12. Okay, that is there for my gradient as simple as possible in terms of h. Right, okay. So again, hopefully you notice in part B why we didn't differentiate the curve, because it's the gradient between 2 points. Okay, between 2 points, the gradient will still be changing y, changing x. Okay. Now, part C then, explain briefly the relationship between part B and part A. Okay, so part A, my gradient at P was 12, right? That's my answer in part A. In part B, my answer was 3h at 12. So it's kind of getting at this idea of h, right? Remember when we looked at first principles, the whole idea was h tended to 0, okay? That's the whole idea here. When h tends to 0, this 3h, that h goes to 0, and I'm left with 12. Well, hang on, 12 is actually my proper answer. So, okay, so what I'm going to say then, the relationship between my two answers is, as h tends to 0, 3h at 12 tends to 3 lots of 0 at 12, because h goes to 0, right? So that goes to, we have 3 lots of 0 at 12, that is 12, which is my answer to A, which is the gradient in part A. And so the idea then is that the gradient becomes accurate, right? And so again, the gradient then, so the gradient of PQ tends to the gradient of the tangent, okay? So remember, what we looked at in part A was the exact gradient of the tangent, right? So if you draw a tangent line at P, that was the tangent in part A, which is what which is what differentiating tells us. It tells us the gradient of the tangent at the point, okay? And then the idea is in part B is that as we move Q as we move q closer and closer to p, such that the gap between p and q, that gap h, diminishes to 0. So p and q are basically next to each other. So the gradient from p to q basically matches the gradient of the tangent, which is the actual gradient that we're interested in. So so that's the whole idea, right? So h is pushed to 0, we get the proper gradient, okay? And so yeah, okay. So that's it for differentiating quadratics. Next time we're going to look at differentiating more types of expressions or functions of x. But for now, I'll see you next time.